Hey everyone, this video is going to go over polarity. Let me go ahead and share this screen here really quick. And so first off, I just want to tell you what polarity means in reference to chemistry. So polar versus nonpolar, it's talking about the unequal or equal sharing or the balance of the electrons within the bond or within the molecule itself. We're going to be talking about both polar and nonpolar bonds and polar and nonpolar molecules. Regardless of what we're talking about though, polar means that there is an unequal sharing or an imbalance of the electrons. And so when you think about polar, I want you to think about, this picture of the polar bear. It has a very small head compared to this enormous body that's very unbalanced. This picture of the seesaw up here, this cartoon up here, where you've got one large bear and one small bear, creating this really large imbalance on the teeter-totter itself. Both of those would represent something that was polar because it's unequal and it's unbalanced. Whereas anything that's nonpolar means that there's equal sharing or it's a balanced all the way around the actual structure of the molecule. Okay, so polar is unequal, unbalanced. Nonpolar is equal or balanced. Okay. So we're going to first talk about bond polarity. Okay, I said that there's two types of polarity. There's bond polarity and there's molecular polarity. So bond polarity has to do with the electronegativity of the atoms within the bond. So if we look at, for example, this structure here, we've got this black atom here and this red atom here. This is a bond. Okay, so we're talking about the bond itself and the electronegativity difference between this atom and this atom, okay? Now, when we're talking about electronegativity difference, that difference, because it means attracting electrons, is going to determine if the electrons in this bond are shared equally or if they're going to be pulled to one side or the other side. Basically, these atoms are playing tug of war with the electrons that are right here. So I like you to picture this. I have a twin sister. Here she is. Me and my twin. If we were playing tug of war over some electrons that were right here, if we're playing tug of war because we're the same, because we have the equal pulling on both of those things, we're pretty evenly matched, we would create a nonpolar bond because there would be equal sharing. It would be balanced. But if I was going to play tug of war with the rock, for example, I'm not going to win. Let's face it. Look at me. Look at him, okay? He's definitely has a stronger electronegativity. He's going to pull the electrons closer to him, and I'm not going to be able to have as big of a pull on those electrons itself because I would have a weaker or a lower electronegativity value. That's what's going to determine if a bond is polar or nonpolar, if those electrons are shared equally between these two things, or if they're going to be pulled more towards one or more towards the other, okay? So we have nonpolar bonds and we have polar bonds. So again, nonpolar means that there's equal sharing. Nonpolar means that there is equal sharing. So in order to have a nonpolar bond, these two things have to be the same. They have to be the same atom, or we can have a carbon bonded to a hydrogen. Now in that case, the electronegativity values between the carbon and the hydrogen are so minuscule that the electrons are shared equally between a carbon and a hydrogen. And if we have two bonds that are the same, or two atoms, that are the same, they're going to have equal pull on those electrons, and the electrons aren't going to get pulled more towards one side or to the other side. Those are the only two types of nonpolar bonds that I want you to remember. If it's bonded to itself or if it's a carbon-hydrogen. Any other covalent bond would be considered polar, meaning that there's unequal sharing of electrons. That means one thing is going to pull the electrons closer to it because it has a greater electronegativity, okay? So when you have a polar bond and something can pull the electrons closer, it's going to create a partial positive end and a partial negative end in that bond. Meaning here, one of these is going to be partially positive and one of these is going to be partially negative because the electrons are negatively charged. It's not going to create full ions because the electrons aren't completely transferred from one thing to the other thing. But because the electrons are pulled closer to one thing, that one thing that they are pulled closer to is going to create a partially negative end to that bond. And the other thing, because it doesn't have the electrons as much, is going to create a slightly positive end of that bond. Okay? There's unequal sharing of electrons in a polar covalent bond. So remember, there's only two types of nonpolar covalent bonds. That's if it's bonded to itself or if it's a carbon bonded to a hydrogen. Any other covalent bond you would identify as a polar bond. Okay? Now with polar bonds, like I was saying, there's an unequal sharing of electrons in the bond. This is going to create a partial positive and a partial negative end. Because it has a partial positive and a partial negative end, it would create what's called a dipole. So let me draw something down here. So let's say we have water. We've got H2O. So water looks like this. Now this bond right here, that's what we're talking about, bond polarity, the lines. This bond right here, is this a polar or a nonpolar bond? Well, it's an oxygen bonded to a hydrogen, so it's not bonded to itself, and it's not a carbon bonded to a hydrogen. So this is a polar bond. That means we are going to create a partial positive and a partial negative end. So which one, the oxygen or the hydrogen, is going to hog the electrons? It's going to pull the electrons towards it. Well, the oxygen has a higher electronegativity, so that means it's going to hug the electrons more. It's going to create a partially negative end of the molecule, meaning the hydrogens are going to create a partially positive end. Okay, so if it was a polar covalent bond, we would draw these dipoles indicating that there's a partial positive and a partial negative end to the molecule. So let's do another one. Let's draw carbon dioxide. We know that carbon dioxide looks like this. And again, with bond polarity, we're talking about right here. Is this bond polar or nonpolar? Well, the bond itself is polar because it's not bonded to itself, and it's not a carbon bonded to a hydrogen. So that means it's a polar bond. So then which one is going to hog the electrons? Which one's more electronegative? The oxygen is going to hog the electrons, so the oxygen would get a slightly negative dipole. The carbon would get the slightly positive one because it doesn't get the electrons as much. Okay, we would not put those dipoles on a nonpolar bond because nonpolar bonds have equal sharing of electrons. Nonpolar bonds would not create a partial positive and a partial negative end. Now we also have polar and nonpolar molecules. Polar and nonpolar molecules, okay? Again, polar means that it's unequal or unbalanced. So when you look at something, for example, like this, remember when we were drawing our Vesper shapes, this represents a lone pair of electrons. You can see how it's pushed these bonded pairs of electrons down. This has created an unbalance of the electrons. So this would be a polar molecule because it's pushed all of these bonds down. And now we have an unbalanced looking structure, okay? Whereas something like this, which is the same all the way around, everything is equally distant apart. This would be a nonpolar molecule because everything is the same. It is all equal and balanced, okay? Let's say though that we exchange this, one of these atoms for this. What if now it looks like this? We've got one blue atom and two green atoms. Is this the same? Is this balanced? No, this is not the same and balanced anymore, so now it would be unbalanced and unequal, so now we have a polar molecule again, okay? When we look at this structure here, is this the same? Is this balanced all the way around? Is this equal? And yes, it is, because it's got the same ends. both red ends, and it's equal balanced all the way around this molecule. So this would be a nonpolar molecule. What about this one? Remember, these little family things, they represent lone pairs of electrons. We've got 2 white atoms at the end. Is this equal and balanced all the way around? No. Even if I take these little lone pairs off, because technically we can't see them in an atom, but even if it looks like this, does this look equal and balanced? No. The reason why it's not equal and balanced is because it does have these lone pairs around the central atom. Okay? So, polar molecules are going to have different ends, or there's going to be lone pairs. Different ends would be what I created here with the blue and the greens. Okay, this would be different ends in a polar molecule because not everything is the same all the way around. Okay, so if it's like this, where there's different ends, or if there's lone pairs, that would be a polar molecule. Okay, but if there are same ends and no lone pairs, so same ends, everything is the same all the way around, and there's no lone pairs, it's all balanced and equal, this is a nonpolar molecule. In order to determine molecular polarity, you must draw the molecule so you can see what it looks like, okay? So let's give this a try. So when we draw PCl3, I'm not going to go through the steps of drawing it, I'm just going to draw them, okay? So this is what PCl3 looks like. We're going to practice bond and molecular polarity. So this is what PCl3 looks like here. So let's first ask about the bond polarity. So we're going to be talking about this right here. Is that bond polar or nonpolar? So ask yourself, is it between 2 of the same atoms? No. It's between phosphorus and chlorine. Is it between a carbon and a hydrogen? No. So this bond is a polar bond. Oops, I forgot the R. Polar bond. It's a polar bond. Which one's going to hog the electron, the chlorine or the phosphorus? The chlorine's going to hog it because it's more electronegative. So the chlorine is going to be partially negative and the phosphorus would be partially positive. Okay? Then let's ask about the molecular polarity. Are all of the ends the same? Yes. Are there lone pairs though? Yes, we're talking about lone pairs on the central atom. Those are what's important. There's lone pairs on the central atom, so this is a polar molecule. Okay, now let's take a look at the next one here. We've got NH4. So I shall draw this really quick. Remember, the hydrogens are not going to get dots. We got to bracket this because it's a polyatomic ion. So first question about bond polarity. We got this bond right here between the nitrogen and the hydrogen. Is that bond polar or nonpolar? Is it bonded to itself? Nope. Is it a carbon bonded to a hydrogen? Nope. So that means it's a polar bond. Okay. Then you're asking yourself about the molecular polarity. Are all of the atoms on the end the same? Yes, they're all hydrogen. Are there lone pairs on the central atom? Nope. So same ends and no lone pairs means that it's a nonpolar molecule. Okay. Let's look at this next example, CH3Cl. Oh, I forgot to draw on my ammonia here, ammonium. Which one's going to hog the electrons? The nitrogen hogs the electrons. Sorry, I forgot to draw these. The hydrogens will be partially positive. This third one, CH3Cl, what's going to go in the middle? Carbon is going to go in the middle. You connect everything else to it with a bond. Doesn't matter the order that you do everything here. So then we ask ourselves about the bond polarity. This time we have two different bonds. We have this bond and we have this bond. Well, this carbon-hydrogen bond, which there are three, that bond is nonpolar. So there's three nonpolar bonds because there are three carbon to hydrogen bonds. Okay, now this bond here between the carbon and the chlorine, is that bond polar or nonpolar? Well, that one's going to be polar because it's not bonded to itself and it's not carbon-hydrogen. So we're going to put dipoles on the carbon-chlorine bond, but not on the carbon-hydrogen bonds. The chlorine is more electronegative, so it would get the negative dipole. The carbon would get the positive dipole. Now let's ask ourselves, is this molecule polar or nonpolar? Well, the molecule, are all of the ends the same? Nope. If all the ends are not the same, that means it's going to be a polar molecule. Okay, let me clear my screen so I can do this last example. And put some dots on here. So the first thing we're going to do is we're going to ask ourselves, is the bond polar or nonpolar? Is it bonded to itself? Nope. Is it carbon-hydrogen? Nope. So we have polar bonds. Between these two, the sulfur and the chlorine, which one is more electronegative? Which one's going to have the partial negative charge because it's going to hog the electrons? The chlorine. The sulfur means it's going to have a slightly positive. Okay, now molecular polarity, are the ends the same? Yes, they're both chlorine. Are there lone pairs? Yes, there's lone pairs on the central atom, so that means it's a polar molecule. Okay, now why don't you give the structures on the next slide a try, and if you have any questions, you can let me know. Okay, good luck.